Good afternoon, everybody, and welcome to the Einstein Telescope Industry Webinar series. My name is Kryoz, and I'll be your host today while we explore how science and business come together to create the technology necessary for Einstein Telescope. In the first episode, we saw the broader landscape of the Einstein Telescope, how it can foster cross-border collaboration and be a driver for innovation. Today, we'll take a deeper look into the engine room of that innovation, and particularly the R&D infrastructures built for and because of Einstein Telescope, because it's at these locations that make it possible to make the technology required for Einstein Telescope. As you know, I will not do this alone, but with a nice panel of experts. Before I join my experts at the table, I want to make you aware of the chat function. During this hour, we will look at your questions, so don't be shy and ask any question you want to our audience. Now let's get started. Welcome everybody, here at the table. Let me start with introducing our guests. First up, Romaine Kunst, thermal systems engineer at DEMCON Kryoz and a project leader for the cryocooler project. Today you'll talk us through your journey collaborating with the ETpathfinder to create a new vibration-free cooling technology, and that will help and bring the Einstein Telescope's performance to the next level. Welcome. Next to you is Pieter, Managing Director at DEMCON Kryoz. You will share the strategic perspective, why DEMCON has joined such projects, long-term collaborations for Einstein Telescope, about your ecosystem and the benefits you already see on your innovation roadmap by participating, as well as the opportunities you see coming in the future. Yep. Welcome also to you.
Thanks for having us.
On the other side, we have Bentvelsen, Chief Science Officer at the ET-EMR Project Office and currently working on the latest technology and scientific challenges.
Thank you.
Welcome. And last, to round off the table, we'll take a look at our ecosystem together with Jordens from POM Limburg.
Happy to be here.
Sam, you will talk us through how the industry, big and small, can collaborate, how they can participate and join or be supported financially. So we're looking forward to that story as well as to the newly launched project Smart Skills Lab, where you will bring us the inside and outsides. So once again, welcome. Let's get started looking at our infrastructures. Because ETpathfinder, ETCRISTAL, and the newly announced ultra-high vacuum lab in RWTH Aachen are all three facilities developed for Einstein technologies, because we need to push technology forward to something that doesn't exist yet today. And these are not just facilities, these are prototypes of the future. They are places where ideas meet engineering, where theoretical challenges become practical solutions, and where scientists and engineers work side by side. They bring together universities, governments, and most importantly for today, industry partners to work together, side by side with scientists. And we're seeing this happening across the EMR region. Companies are entering consortia, new business cases are being developed, and MOUs being signed with knowledge institutes, and engineers are working with physicists in all of these labs. And these labs will not only serve Einstein Telescope, they have a broader impact and will have spillovers into airspace, life sciences, and other fields, which we will see today as well. But first, to give you a better understanding of these facilities, we went to the project leaders that actually lead these facilities to tell us all about them. So let's have a look at the video right now.
Welcome to ETpathfinder, our test facility for Einstein Telescope technologies. In the clean room behind me, we do incredible sensitive length measurements in order to understand better the universe. And I would invite you for a tour with me downstairs in the clean room to see what it is all about. ETpathfinder was set up in 2019 here at Maastricht University and is in collaboration of about 25 research institutes, university from 7 European countries, all working together to make this test facility kind of a focus point for European research.
Welcome to the CRISTAL laboratory. So CRISTAL stands for Cryogenics and Inertial Stability Laboratory. It's a lab where we develop a huge prototype dedicated to develop the technology for the Einstein Telescope. In the Einstein Telescope, we will need very large mirror cooled down at cryogenic temperature. And this is all what this prototype is about.
So the specialty about ETpathfinder is that we have a full interferometer configuration which allows us to do a length measurement at the thousandth of a proton diameter. Currently operating gravitational wave detectors LIGO and Virgo, ET aims to work at cryogenic temperatures, use different materials, cool the mirrors which are used for this measurement down to minus 260 centigrades. And these technologies are tested here. And at the moment, we don't know of another place in the world where you can actually do these tests at the sensitivity level we are aiming for here.
One of the key specificities of this e-test prototype is that it's at full scale. So we are talking about large mirror. So thanks to that, we can really test some technology which are directly relevant for the Einstein Telescope. We combine in this prototype an active isolation with an inverted pendulum. Thanks to this hybrid isolation system, we are capable to stabilize the mirror and virtually disconnect it from the ground down to frequencies as low as 10 millihertz.
In order to achieve this incredible sensitivity of 10 to minus 18 meters or thousands of a proton diameter, we need to push technology beyond the state of the art in many different fields, like optics and lasers, seismic isolation, sensors, controls, but also topics like vacuum, cryogenics, vibration-free cooling.
Another key technology that we are implementing in this prototype is the radiative cooling strategy. So we want to cool down the mirror, but we don't want to degrade the isolation. And that's the reason why we test the capability to cool it down without touching it, which means using radiative technology.
The Einstein Telescope will work for 50 years. And over 50 years, technology changed a lot around us. So what we will do actually is once we have demonstrated the first version of the Einstein Telescope technologies, this place will actually move to test the second generation and the third generation. So probably every 5 to 10 years, a new generation of technology will be tested in ETpathfinder for the next couple of decades. ETpathfinder is an open collaboration, and we invite everyone from industry, from research institutes to join us here in the endeavor to make ET technologies reality, validate them, and in the end make the Einstein Telescope possible at all, which is really our dream, to be able to look back towards the Big Bang with the Einstein Telescope, understanding what the universe is really made of and what are its constituents, from black holes over neutron stars up to supernova, dark matter and dark energy.
Yes, exciting stuff and wonderful to see. Also, big thanks to our professor Stefan Hild from Maastricht University and Christophe Collet from Liège for welcoming us and showing us these facilities. Stan, let's move over to you. Welcome once again.
Thank you.
Maybe to start, what does a Chief Science Officer at the Euregio Maas-Rijn Project Office do?
Well, you see, the project office is actually quite a large group of people in Maastricht looking toward the challenge of seeing if we can actually build the Einstein Telescope in the EMR region. So we are doing a feasibility study, and that means studying the underground, studying the seismic vibrations in the environment, and then also the impact on the instrument, which is quite a complex calculations. And so this is what we are doing in this project office, and so I give also, I'm part of the directorate for that. But it's more than that, because we also are proposing in the international arena the Einstein Telescope. So maybe you know, we have discussions like, is a triangle optimal, or should we make an L shape, two L shapes? And we think that the triangle is the best option for the next generation gravitational wave telescopes. But this is something that is also happening in the international arena. And so that means that we have to combine all our efforts. So we have combined all the universities and institutes together in what was also mentioned here, the MOU, to make sure that we all look toward this one big proposition of a bit book. By the end of next year, we plan to deliver a bit book where we condense all the information on how beautiful the environment is to host the Einstein Telescope.
All right, thank you. Yeah. Now you're now in your role in the project office, but before you've been the director of NICAF, you've been associated with CERN. Yeah. So you must have seen many of these type of facilities like Pathfinder, like Cristal before. Or are these actually unique places?
Well, you know, if you go to CERN, and that's an amazing world laboratory, and with very high tech and an immense amount of technology. We say the Einstein Telescope is a bit like the particle accelerator, the LHC, without a beam, because you need, vacuum systems. You need to go underground. You need high-tech environment. Every part of the system should work toward each other and combine to make everything work. So the technological challenges are very, very big there as well. But I must admit that looking at the Pathfinder and ET-CRISTAL, and now I also hope that the Vacuum Lab in Aachen, those are test facilities which I haven't seen so big for earlier at CERN. It's really amazing, but the technical challenges for the Einstein Telescope that the Pathfinder is facing are huge. So I think it's fully justified that it is there. But I must say, I find it rather unique. Yeah.
And then also critical to address the technology.
No, absolutely. The whole point is to reach the sensitivities that Professor Hield was talking about, and for that all the components should be working. So I see the ETpathfinder really as an integration center where you can test various advancements in technology and to put it together to see if it actually works. So you validate the technology in the Pathfinder, and that's a very important aspect.
Yeah. So in those parts, those are often also called subsystems. Yeah. Could you share an example of a subsystem or a challenge that was tackled already at Pathfinder or Cristal?
I think there are various examples. There are various roadmaps in technologies, and I think we will be hearing about one or two of them later this afternoon. But maybe to mention one is Janssen Precision Experiments. JPA. They did quite a bit of at the very last moment inside the cool box, inside the cryogenic system. In the very last moment, where you have the wire that holds the mirror, to have an active damping system installed, and that has been designed and implemented in the Pathfinder, and the papers have been written, and you see that it actually works, and you gain a factor or an order of magnitude, let's say a factor of 10 or so, in the dampening the vibration, and that's a very important step. So I think that's a very concrete, real example of what's going on there. Yeah. And that means that also it's not done yet for the Einstein Telescope, because then you have to again try to get an order of magnitude. But I think this is a continuous effort that will go on for many, many years.
Yeah. And also a nice example for our other guests who are building some of the cooling technology that will then literally be linked to such an actuator,
Exactly.
damping the last steps of the cooling technique.
Yeah.
So then maybe looking at Cristal and Pathfinder, Cristal, which we saw Professor Christophe Collet mention, uses a radiative cooling system.
Yeah.
We see, or we'll see later today, DEMCON showing us how they are working on a vibration-free sorption cooling technology. Those are in competition with each other. Is that strange to do, or is that actually normal in this field?
I would say this is quite normal. We need competition in order to get. This is really Champions League technology, and you don't know beforehand which one will be the best. So there is also R&D, trial and error, and see which technology will be at the end of the day the best one. And so it's also at CERN, for example, for the Atlas detectors or for technology for detecting these particles. There were competing technologies developed simultaneously, and then at some point the collaboration or the somebody has to decide which one will be applied in the real Einstein telescope. But I would say just go as far as you can and make sure. So, for example, this E-test radiative cooling is indeed in direct competition, I think, with the proposal from DEMCON on sorption-free cooling, and so we have to validate both technologies and see which one is optimal.
Yeah.
Certainly, yeah.
And I guess some, speaking to the business developers, even if a technology doesn't make the cut in the eventual design of Einstein Telescope, I'm sure you will guide that technology to other industries as well.
Yeah, I think a company that wants to innovate for Einstein Telescope always have to think about a second business option, because, well, sadly there won't be 20 or 30 or 50 Einstein telescopes. So if you develop this technology, you should think about another market that's not Einstein Telescope. So I think we focus on innovation within technologies in key technology domains like cooling, like vibrations, and then we will see where they end up in industry, and we'll see what kind of
for
impact
us
they can reach.
specifically, we already were working on vibration-free cryo cooling in our products. Basically, we are making the next step, basically, to upgrade the technology to also work for Einstein's telescopes specifically. So then, so that's our second, let's say, business. It
I
was
think
our
it's
first,
a very
basically.
important notion that there are other.
And don't bet on one horse. Also, I would
Yeah.
say. So that's a little bit tricky.
Okay, well, great to hear. Just looking at the audience and seeing if some questions for Stan are coming in. First one would be if you can briefly explain how Pathfinder and Cristal complement each other and not just are maybe in competition on technology, but also how do they complement each other?
So at the end of the day, you want to have a mirror in the Einstein telescope that doesn't vibrate at all. And the boundary condition is that you want to cool it in 230 degrees below zero. And so how do you do that? So you cannot put a refrigerator on the mirror itself. So so the complementarity, I think, is the way in which you want to cool down the mirror. Do you want to do it with radiative cooling, which Christophe Collet just explained? So that means that you basically put it in a black body radiator and just let it radiate until it's cooled down to the temperature you want. So you wait. Or do you want an active cool system and then do it via the suspension?
Yeah. And both have, let's say, the advantages and disadvantages.
Yeah.
All right, thank you. Let's move on then to the next section and looking at the practical side of things. Romaine, I introduced you as thermal systems engineer at DEMCON Kryoz, but you're also the project manager of the CryoCool project.
Yes, exactly.
Could you tell us a bit more on that?
Yes, happy to. Yes, so I will tell a bit more about the showcase of today, which is the zero vibration cryocooler. As already was mentioned, both Pieter and me, we work at DEMCON Kryoz, which is part of the DEMCON group. And DEMCON is an engineering company that is specialized in developing and producing high-tech systems. We do that together with almost 1,200 employees, and we are spread over 25 companies in 7 different locations. As you can see on the slide here, I displayed 5 different showcases, and for today I will be going into detail for the vibration-free cryocooling for Einstein Telescope. And in this consortium, we work together with a company, Cool, based in Hengelo, and with University of Twente, which is right across the street from us in Enschede. But this consortium also relies on a big heritage, which I want to demonstrate with this roadmap. So there are a lot of details here in this roadmap, but what I mainly want to demonstrate is that this engineering path already started back in 1995. That's where the research and development started of disruption cryocooling technology. Around 2008 and 2009, there were also 2 industrial timelines. And now with the zero vibration cryocooling consortium, we were able to bundle all the timelines together. And the aim for us in this technology domain is to bring sorption cryocooling to the next TRL level. So why do we need a cryocooler for Einstein Telescope? I want to demonstrate that by using this sensitivity plot that you can see here. In here are the sensitivities of the existing detectors plotted, and what is mainly important is that a sensitivity improvement is aimed in the low frequency region. Well, Kaga was the latest detector, and that was also the only detector which already has cryogenically cooled optics, and they use a pulse tube cooler to do that. And as you can see, the aimed sensitivity improvement for Einstein Telescope is about 3 orders of magnitude bigger than was aimed for Kaga. And how to do that? Well, you have to reduce overall noise, and you can do that by reducing seismic noise, by placing the detector underground. You can reduce quantum noise, but more importantly, you also have to reduce thermal noise. And in order to achieve that, you cannot reach this with traditional coolers, so you need this new vibration-free cooling system. Well, first, I want to highlight that we will use the ETPathfinder facility, which is an initiative by NICEF and Maastricht, as was already mentioned. We will use this facility to technology benchmark our sorption cooling technology. We will implement 2 cooling systems at the ETPathfinder facility, and we will also implement 1 cooling system at the high pressure lab at University of Twente. So what are the main requirements that our cooling system has to meet? Well, first, the cooling power, we have to deliver 20 milliwatts at 8 Kelvin. And how can we achieve that? Well, first, we will use a Joule Thomson cooler to meet this requirement. Then, of course, the vibration requirement is also very important, and the biggest vibration mitigation is actually that we will not use a mechanical compressor, but we will use a sorption-based compressor, which I will explain later. And another important requirement is that we have to reach cool down within 4 weeks, which, as you can imagine, if we have 50 milliwatts of cooling power, then it is quite challenging. So that's why we have a Kickstarter system, which has about 250 watts of cooling power at room temperature to help pre-cool all the relevant thermal masses. So what is then our solution? So the system baseline is that we have this sorption-based 3-stage Joule Thomson cooler. In here we have 3 stages with the 3 different working fluids. We will have neon, hydrogen, and helium will then go to the lowest temperature. So at the end, there will be a thermal connection between this 8 Kelvin platform to the final mirrors of ETpathfinder. And for the sorption compressor, this is actually filled with active carbon pills. And the active carbon pills have the special property that when you make them very cold, for example, to liquid nitrogen temperatures, is that they can absorb a lot of gas particles onto the surface. Then we have a heater placed inside these pills, and when we then heat up the sorption pills, then the gas particles will desorb. And since we have placed these pills inside a container, that means that this way we can establish a pressure increase without having a mechanically moving piston. So it's thermally driven. Then if we move over to the conceptual design, so in here I want to demonstrate a few challenges and competences that we have. So in the system here you see the compressor system, the cooler system and the Kickstarter system, and the 2 blue circles in the middle are the mirrors. So as you can see, one challenge is that we have to cool these mirrors to minus 265 degrees, 10 Kelvin, in order to reduce thermal noise. As I mentioned, we will do that by using the Joule-Thomson cooler. Then we had to define also another cooling strategy, and that is mainly focused also on this Kickstarter system, which will help us pre-cool all these relevant thermal masses from room temperature to cryogenic temperatures. Then another big challenge was the vibration-free requirement. As I mentioned earlier, we have this sorption-based thermally driven compressor, but we also mitigated multiple other vibration sources. So for example, we aimed to only have laminar flow, we have smooth bands in the system, and there are many more other things that we implemented. Then also inside this vacuum tower, we have extreme vacuum conditions. That means that you cannot select all the materials that you want, and there's a big cleanliness requirement. As I mentioned, we also work with hydrogen, and that also imposes that it has to be safe. So that was also a challenge. And at last, since we cannot first build a prototype on the scale, we basically built a model of this complete system in order to make sure that we are building a baseline which will then meet the requirements. So as you can see in the plot in this slide here, so inside this model are all the details of the complete system, but with this model we know that with the chosen dimensions and temperatures and pressures we are able to deliver this cooling power. Then I want to transition from concept to detailed design. So quickly highlighting in here, this is a picture of what a heat exchanger then looks like. We have parallel lines to ensure laminar flow. Then you can see in this picture here that really all the bands in this system are following a certain criterion, such that we only have smooth bands, again to prevent vibrations. And this is what our liquid nitrogen vessel looks like. So we have sufficient area to prevent violent boiling inside our liquid nitrogen vessel. Then I want to transition to the complete detailed design. So this is a picture of what our final system then will look like. And here I have a GIF that then demonstrates all the different assembly steps. And in the right picture you can see the mirror tower in the ETpathfinder facility, in which we will implement our sorption technology. So that was my talk, so thank you for listening, and with this I conclude my story.
Thank you, Romaine, for this presentation. Please join us back at the table to see any questions coming from the audience as well. And while Romaine joins us, I'll transition to you, Pieter. Managing Director at DEMCON Kryoz, over 17 years involved in the company. You must have seen a lot, a wide experience also in thermodynamics, cryogenics, microfluidics and modeling. So take us through a day at DEMCON and what DEMCON does otherwise.
A day at DEMCON, yeah. Well, basically, this is the stuff we do day from day to day. I think the Einstein Telescope project is really an example project of many of the stuff that we develop for our clients. So as Romaine said, DEMCON is a contract R&D company. So basically we solve challenges for our clients in a broad application fields. From semicon to space applications to high-tech systems to a lot of life sciences and health systems, also medical equipment. And we do this usually starting from a low TRL level. So like this project, so nothing exists, or only an ID exists. And then we start engineering, and that's what we do.
And then you mentioned contract R&D. In this case, you also joined a consortium working on a cryocooler for Einstein Telescope. Some already said there won't be 50 of these devices. So why did you join such a project?
Yeah, first of all, we got in contact with this project through the University of Twente, as Romaine already mentioned. That was already, I think, 4 years ago. So when the idea popped up to build a cryocooling solution specifically for this project, we already worked a lot with the university, and then get hold of this idea. And basically, we also we do both contract R&D and product development. And our own products are really focusing on zero vibration cryocooling. So that's where the actual match is, but we do it at a very small scale. So this was a good opportunity for us to see if we could, let's say, upgrade our systems to a larger scale, first off. Next off, we are always interested in these man on the moon type projects. That's really our cup of tea. Also, it really gives and motivates our engineers. And a project like this is really, a really good showcase for us that we can use also in our marketing tooling. So usually when we go to a potential new client, the first thing we show is this project, I would say, and because it really shows all our different competence fields and how they come together in realizing a project like this.
So it opens new doors and opportunities for the company. Can you share a concrete example of how DEMCON is already benefiting from the Einstein Telescope?
Yeah, I think there are already several. So one of the most, let's say, obvious ones is the field we're already working in. So that's building coolers for electron microscopes, also very sensitive equipment where you're looking at nanometer level, not at this as Stefan in the introductory video said, I think 10 minus 12 meters, which is many orders of magnitudes less. But also in this field, zero vibration cryocooling is crucial to do investigations to bacteria, viruses, to develop vaccines like they did for the coronavirus. So they also use cryocooling there to basically fixture the samples and look at them with an electron microscope. But also there they're looking to the next level. So we work in what they call scanning electron microscopes. It's very high resolution, but it can be even better when you go to transmission electron microscopes. And there you really have to go to also pico level stability. And then we have to upgrade our technology to this level of vibration. And I think the things we now learn in this project can be directly applicable in this for this next generation of products, basically. So that's one of the examples.
So improving healthcare with Einstein Telescope.
Yeah, for example. I think another one is quantum technology. That's also something we are now really active looking into to, let's say, building cryocoolers specifically for this field. And there it's more or less not so necessarily the vibration, but the very low temperatures that we can go through. And using this, let's say, this approach with this Joule-Thomson multiplied system, basically is a kitchen refrigerator. You use high pressure gas and you expand it. So basically the principle is very simple. But then we have to downscale it to a real small product that they can use in field to cryocool, let's say, quantum devices. Basically, there's no quantum technology without the cryocooling, so that's also an enabling technology. And now we're looking into downscaling this type of cryocooler to also be applicable in quantum technologies, and for us that can be a future product.
And usually important for the autonomy in Europe as well, that we have
certainly
technology in
that's
Europe.
A good point, because currently all the cryocoolers for that specific field are basically built in the US and Japan. And so if we as Europe really want to focus also on this, not only on the quantum side of the devices, so the qubits and SNSPDs, these kind of devices, I think we should also focus on, let's say, the enabling technology of the cryocooling, because one cannot go without the other to go to the next step in quantum. And then I think we should also make some effort in building this next step of cryocoolers within the European Union.
Great. So let's talk also about the Pathfinder shortly.
Yep.
Romaine already said we'll be doing the verification step there. What does that mean from a business point of view? How valuable is it to have such a facility where you can actually test your solutions?
Yeah, so if you look into the industrial steps you have to take from, let's say, ID to product, you have, of course, all these TRL levels, which most people are familiar with, I guess. But certainly, it starts with an ID, and then you have to prove that it works in a relative environment. So for us, of course, we cannot build such a huge setup with ultra-high vacuum, the lasers, to prove something stands still on this type of this level of magnitude in terms of vibration. So I think, the ETpathfinder also Maastricht, where we will test our setup, that's a direct, let's say, test if your new technology actually works in the environment that it's supposed to work in. This gives us really the opportunity to prove that, and that's also, of course, also for our own technology, very crucial.
Romaine, I can imagine you're working a lot with scientists in ETpathfinder. How is that, like a commercial company working with scientists in one environment?
Yeah, I really like the collaboration. So as you mentioned, people have different backgrounds, either from industry or from academic. But what I really like is that everyone has the same goal. So everyone is really motivated to make this a successful project. And I think that's very inspiring. And I think everyone has their own expertises. And I think we found a way of working that works for everyone. So I really like it.
All right. So the consortium is developing technologies that will ultimately scale to the full Einstein Telescope model. What's already a key insight or breakthrough from the project so far that even surprised the engineers at DEMCON?
Yes, so I think there have been multiple milestones and also milestones to come. And I think what is really nice of this project is that it is the first time that we are combining the sorption technology and the Joule-Thomson technology on this scale. So once we have established that, I think that's already a very nice milestone. And I think for us, for last year, what was a milestone is that we were able to create this model that includes all these details. So it's not like a standalone model of just one stage, but they're all coupled to each other. They're coupled to the sorption cooler, and that was quite a challenge to make it work. But once we were able to do that, I think that was a nice breakthrough, I think. Yeah.
All right. Any challenges from a business point of view, Pieter?
The project, well, so many.
So many.
I think, so one of the things, of course, in these type of projects, you have to collaborate with institutes, academic institutes, and with, the industrial focus is usually also, besides, let's say, the technology goal, it's also the time budget planning, which is very important, and the systems engineering, which is basically the core of our business. So how will you go from the ID to the actual product? And there you see a little bit of, let's say, focus difference between the academic world and the industrial world. So I think also when we joined the project, we really saw that we could also add some value there. So let's say in the project management in general, to see, okay, what do we got? What are all the stakeholders, forces working on the project? How can they be combined within time and budget to reach the goal within the limit, basically? Yeah. So we have 3 years, and then it has to be finished at least for this part of the project.
Are you then steering the scientists as well?
Yeah, well, that's very hard.
Yeah.
As you can imagine. Yeah. But we are trying to, and that's certainly also, I think, on the, let's say, the systems engineering level to see what is the basic architecture of this system. How are the interfaces defined, and somebody over there is working on this, somebody else is working on something totally different. Everything has to fit together. I think we can also, as DEMCON, have some added value there, because that's our day-to-day business, basically. But the acceptance, that's a little bit difficult, of course.
If you could mention like one key skill that an academic maybe should have when working together with industry, what would that skill be?
Key skill, you mean? So I think in the end you're doing it together, right? So then you have to learn from each other and be open also for suggestions, and I think where we are now, we see really that it is changing a bit. So I think, and I think in the general sense, it's very important for the project to be successful. And I think then also a project like this can be, let's say, a key example of how we should approach this, I think.
But the other way around maybe is also true, that you learn something from the scientists.
Of course, yeah,
Yes.
of course, yeah. Well, you know, if you see the achievements, it's incredible. And even of the basic, I have applied physics as a background, of course, but the whole fundamentals is also not fully clear to me. But extremely interested, and also the environment to be able to work, you know, in these clean rooms with these huge UHV setups. That's really impressive, and of course really motivating also to work.
Great. So I'm quickly going through the questions from the audience, and there's one for Pieter Orston actually. How can systems engineering help in the design of the Einstein Telescope?
No, you
I already mentioned it a bit.
Yeah,
So,
but I think also like in the beginning, so how we started is we had the system architecture with like 21 very clearly defined interfaces, and I think still up until now that picture really helps. So in the beginning, it made it very clear like what is an external interface and what are we going to do, but now also for tracking the progress, we still use the picture to see, okay, are there any showstoppers there? What is something that we really need to focus on, or otherwise we have problems when we start implementing things in ETPathfinder. So I think, skills like that from the systems engineering, it really helps structurizing.
If you take up projects like this, basically it starts with the system engineering. So what do you want to build? And then take it apart basically in all the subsystems, and how will the subsystems talk to each other, and how do they rely on each other. And if you not define that at the beginning of the project, you will maybe still succeed, but will you take much more effort, thus money also, to get your goals in the end. So I think
so it's true collaboration between the scientists and the companies.
You have the same goal in the end, so that's good.
Good.
Yeah.
So then looking at companies who are interested in this showcase, but also just participating from their own fields, any advice on how to get involved?
Well, for I think the bigger companies is already, I think, quite clear how to get involved. It's mainly, I think, the smaller SMEs type of companies who are, you know, if you are only 8 people with core technology, which can be very, very valuable for Einstein Telescope. I think for us also in the whole endeavor of getting to our setup, getting, you know, parts like check valves that are cryogenically compatible, for example. So that's not our core business, but maybe there's a smaller type of business out there that does only that. So I think if you join, you can learn a lot, first of all. It's very good, of course, also for your network, both technical network and academic network. So I would say, if you're interested, just reach out, and like we did. And in the end, we contacted, for us, it was Leof, of course, to get in contact. And I think we have the same type of institutes in Germany and Belgium to do the same.
In Belgium, the Netherlands, and Germany, there are business developers active across the whole region. And we also sit together every 4 weeks to discuss like questions from companies, new project ideas, engineering challenges from the Einstein Telescope. So if you're just interested, let us know, and we will find a way to maybe get a project out of it.
Yeah, thank you. So I see there's also some technical questions coming on in the chat. For those to not dive too deep into this technology, I want to also make you aware of the recent article published in DSPE Micronique, where a detailed design and fundamental research is also discussed. So find the website of DSPE and you will find a lot more information, or just reach out to Romaine or Pieter directly. Contact details will be shown at the end of the webinar as well. So with that, let's move on to the last topic of today, the ecosystem. Sam, a business developer at POM Limburg, as we already said, and together with the regional partners, you play a key role in connecting and making the links between companies and the R&D challenges. What are you hearing? What's the buzz that companies have right now?
Yeah, so the last 2 weeks I had the opportunity to visit some fairs and have a booth at them with the Einstein Telescope EMR consortia. One in the Precision Fair in Den Bosch and the other one Space Tech Expo in Bremen. And we met with companies across Europe there, especially in Bremen. It was a very international event. And we really felt the excitement for the Einstein Telescope because there's a lot of political clout about it. So companies really have the idea that, maybe it will not be here, but it will be somewhere. The Einstein Telescope is a science institute that will be happening somewhere in Europe in the next years. So they're really excited about that opportunity. But then also come the questions, because, well, the engineers, they are very excited about just the fact that we're trying to measure such small distances. They're amazed that it could be possible in, the next 10 years. But then it's also a question about how does my business model work with this thing? Because, for example, you mentioned that you're an R&D contractor.
Yeah.
And then we ask as business developers, you have to put in a part of your own money into this project. And you're saying, yes, but my business is doing this kind of thing 100% funded. How can we match this? Where are the opportunities? How can we get more out of it than we put in? Because, of course, companies, they want to make money. And I think that's mostly the thing I get questions about is not, I don't really know it or I don't have a technology. More like, how can I become part of Einstein Telescope and have a viable business? And I think that's a very interesting discussion. Yeah,
and to mitigate that financial part a bit, there's also several programs that are already running regionally, but also with Interreg and regional partners. Can you mention some of those?
Yeah, so business development in Einstein Telescope started around 5 years ago with ET2SME, in which 14 companies collaborated to develop proof of concepts for technologies for the Einstein Telescope. And since then, it has really grown a lot. I think at the moment we're at like 85 companies who are participating in Einstein Telescope technologies. And we noticed first a lot of interregional collaboration, then more regional funding, like in the Netherlands coming up. But now we're starting that this interregional cooperation is picking up again due to two projects from Interreg. One from Interreg Meuse-Rijn, the STIP project, in which companies from like 50 kilometers across the Einstein Telescope potential host site can collaborate together. And another one is the COMET project, in which companies from the Netherlands and Germany can also collaborate with each other to develop these new kind of technologies. You can get around 50% funding if you want to collaborate from the European Union, and then the other part is, of course, for your own, and you have to have a business model for this part. Thank you.
And business developers also support with that?
Yes. You don't have to have a complete consortia, you just have to have an ID, and then we will help you find the other companies that are necessary to build a consortia. So that's also very important to take away. Companies usually work together to develop those things. Even you guys with Cool, it's never something you do alone. It's often something you do together.
How important are the border lines between the countries?
We notified sadly that there is still a border. We hope that with the Einstein Telescope this border will further decrease. But like just things like legislation or like working culture or small things really still are a border. But we noticed that like a moonshot project like the Einstein Telescope is often a thing that you can use to smooth those borders over and reduce their impact a bit.
Yeah, and a testament to that is also that recently some of the submissions that business developers guided through were consortia of actually a Dutch company, a Belgian company, or actually two Belgian from Flanders and Walloon, and a German. So that's really the EMR in one project, which is a huge testament also to the work of the business development crew over at the EMR project office. All right, so what would you want to say to companies or SMEs who want to participate but don't know where to start? What would you generally do?
I think we have a great website, the ET-EMR website. I think all the technology domains are explained there. So if you don't know for sure if your company is a match with a different kind of technology, look there. But even if you're not sure after reading the website if it's a match, just send us an email, then we will look at it. We will see what kind of funding opportunities might be available for you. For example, STIP, a new call is opening in less than 2 weeks. So there is, there are opportunities right now to participate. So just send an email to the general email address or just on the business page, and we will reach out back to you to see what we can do.
All right. That sounds inviting. But besides just matching companies to challenges, Pom Limburg also looks at the broader economic impact of the project and of the Einstein Telescope. The large valorization and sometimes, as it is sometimes mentioned, how do you see ET contributing to long-term regional competitiveness for the EMR region?
I think in the beginning we did several regional economic impact studies. There will be a bigger one coming out for the broader region. But I think at the first point we focused a lot on like the employment. We talked about job years and how many people can work at the Einstein Telescope, and well, this is a reality. There will be people working at it, especially during the construction phase. A lot of people will find a job, but of course these are temporary. And this is like the first order economic impact, which is there, but it's not the biggest one. We really noticed that if you want of what the big economic impact of big science is not the direct jobs it creates, it's the indirect impact. Like you're supporting innovation. You're taking companies who may have wild ideas and supporting them to make a product out of it, and which they hopefully can sell to other markets. But you also increase the interest in STEM education. We really notice that at CERN, kids are excited by studying the universe. And if studying the universe happens to happen in their backyard, they become more interested in science. And well, jobs in STEM, they also have very high productivity. So by increasing the amount of kids who want, because of the Einstein Telescope, want to become a scientist, but maybe never end up at the Einstein Telescope, they still contribute to economic growth. And that, especially from these impact studies, was like the biggest impact of big science projects, was like the innovation and patents and spin-offs, of course, but also like the increase of people who want to do science and want to engineer things and make things. So yeah.
I see Pieter nodding.
Yeah, I think so. Of course, these projects like this also they attract highly skilled people, of course, and then you get this ecosystem. That's one of the main also issues of challenges we have is also attract highly skilled personnel. Of course, you see it's the same with ASML. They have to do their best to get the best people towards that region. And I think a project like this also really helps with that, of course, that you attract that person.
The whole world will know the Einstein Telescope.
Yeah, of course.
Yeah.
Cool. So then, looking at the landscape today, is there an industry niche or capability that business developers are currently looking for?
I think a lot of technology domains, we have a very strong region for it. I think the Meuse-Rhine region is like in the heart of industrial Europe. But there are some things that we have less experience in or are still looking for it because, well, I think it was mentioned here before, we are playing the Champions League. So we will need to look across Europe to find companies who can work on this level. So I'm pretty sure that there are some gaps still left. They are definitely not all filled out. I do, however, think that we in the region have the capacity to at least participate in these kind of projects, either as a subcontractor, either as a supplier, or as somebody who pulls a project, but with the help from some European friends. I think that is not a problem, but if we want to be able to do that, I think, great question. Yeah, we have to have the people that are able to work on these projects, because the Einstein Telescope will come like a big shock to the region, increase the demand for certain profiles, and then we as a region need to be ready to supply these profiles, because otherwise, we will not participate in the projects because we don't have the manpower for it.
So I can imagine with STEM research, those people will come, but that will take time. You may also want to train the current workforce. For that, I heard there's a new Interact project called ETPathfinder Smart Skills Lab.
Yes.
Can you talk a bit more about that?
Yeah, so ETPathfinder Smart Skills Lab is a project supported by Interact Flanders Netherlands, but also with participation from Aachen. So a large part of the region is in this project. And we want to build upon the amazing R&D facility that is the ETPathfinder. A lot of so-called ET technology experts are working there on the technologies that will be needed. But we also want these technologies to go back to industry, so that they can benefit from these R&D research. We call it research valorization. It's very important. In the Draghi report, it has been mentioned a couple of times. So we want to translate with this project the technological developments of the ETPathfinder to industry, and also help the current employees of SMEs to be able to take up this knowledge. Because for big companies like DEMCON, maybe most of you guys have maybe a PhD or an engineering degree.
Yeah, a lot of them.
But in smaller companies, this is often not the case. But of course, this is a huge pool of companies we also want to have participating in the Einstein Telescope. And that means that we have to upskill the current employees that are already there in new demanding technologies like optics, like working with vacuum under cryogenic conditions. So we will have to make some workshops to go from graduate to master degree of these existing employee base we have in these very innovative companies, but who might need a little push to get on the championship level that is the Einstein Telescope.
Okay, so any timeline when those workshops will start?
So we are currently hiring the ET technology experts. They will be postdocs working at the ETpathfinder. I hope they're hired as soon as possible, but we will probably start with workshops in Q3 of next year or maybe late Q2. So like, let's say in 8 to 6 months, we will have something on the table. But if you're interested, you can reach out right now, because we are asking companies, what are the difficulties you are hitting today? And then we can also help this input to shape the workshops that will happen in 6 months to a year. So feel free to reach out, and we are happy to collaborate.
All right, cool. Just checking if there's any questions from the audience for you, Sam, and otherwise we'll also have some time for questions from for the other guests. So maybe on testing in these facilities, can companies also test or validate their own technologies?
I'm not an expert at what is possible at ETpathfinder or ETCRISTAL. I know a lot of collaborating research institutes have smaller scale testing infrastructure that you can use to test sub-components. I think for like, if you have a very big thing and it needs to fit in the ETpathfinder, it will be a bit hard because we already have a cooling setup in it or a laser setup. So it would depend.
But it's
on
a very open collaboration.
Yeah.
So indeed, if there is initiatives, then I think you should contact Stefan Hielten to see how it can fit in. And this is one of the ideas of the whole ETpathfinder as an integration center for testing new technologies. So I agree, it should fit somehow. But if it does, then I think you're very welcome.
And I think the same goes for Crystal and for the recently announced ultra-high vacuum lab. All right, so then it sounds like the ecosystem is already pretty strong, but can always use more power to tackle any other challenges that Stan might come up with. Looking at the time, it's the hour has flown by, and I have to start to wrap up to make sure we finish on time. So thanks everybody here at the table for joining us, telling us all about your projects, about how to get engaged and all the work happening at the science side of the project office. Thank you also for the audience, for your engagement, for your questions and for your contribution. We will make sure that any questions that aren't answered yet will be answered later. And if you want to join, if you want to get in contact with Sam and his colleagues, please scan the code or go to the website Einstein Telescope EMR.eu. You will find all the information you need there to find your representative in your region, in your language, to make sure that we get you on board of this fantastic ecosystem. On behalf of the entire EMR business desk, all the parties involved, I want to say thank you very much. We will be back in March 2026 with a new topic and a new ET-EMR webinar. And until that time, I would like to thank you, have a good evening, and take care.
Thanks.